Hello everybody, and welcome to this webinar on getting performance from OpenMP programs on NUMA architectures. So this webinar is part of the project POP, which stands for Performance, Optimization and Productivity. And my name is Christian Terboven. I'm leading the HPC team at RWTH Aachen University in Germany. I'm also, since 2006, a member of the OpenMP language committee, pretty active in this context and working on affinity support for OpenMP, and this is why I will give this topic on OpenMP and performance optimization on NUMA architectures. So let me switch to presentation mode here, sorry for that. Why is this topic OpenMP and performance on NUMA so important? So we see on the one hand many programs performing really well on current systems, and I will illustrate in a second that almost all current systems are NUMA systems, and I will explain what NUMA is. But we also see that many people run into performance problems and attribute these issues to OpenMP as a programming standard or the complexity of system architectures. And it really is a challenge to optimize your program, but the problem is not so much attributed to OpenMP programming in itself, but really that programmers have to understand what's going on and that they have to learn about the tools that are available. And with that, my intent is, or with this webinar, my intent is to give you an overview about what is available and what you as a programmer has to do, or let's say even a user of an OpenMP program, so that you can try to attack this challenging problem. So OpenMP and in fact all other threading models like Intel threading building blocks or PPL or POSIX threads or whatever you might use are in particular are very sensitive to NUMA effects because they exploit the shared memory of current systems. But NUMA is a property of an architecture that you have to deal with even when you use MPI programs. So let me explain what NUMA is. NUMA stands for Non-Uniform Memory Architecture. And the CC stands for cache coherency. So that means, or that's a standard on current systems, that if you have a multi-socket system, you will find that the system memory hierarchy is non-uniform, and still it supports cache coherency. So in the context of NUMA, we talk of what we call a locality domain. So if you can see my mouse pointer here in my picture, I'm trying to illustrate a system with two sockets. So this is a dual core socket, and this is a dual core socket. And you see that this socket has a locally attached memory, and the other socket over there also has a locally attached memory. The technical explanation behind that is that the memory controller moved, if we look back a few years, from the chip set into the processor. So that means this multi-core processor has one or possibly multiple memory controllers, and as a result the main memory, the physical memory, is partitioned. So it means we still have a shared memory system where you see, for example, the whole 128 gigabyte of memory as logical memory that you can allocate and work with, but underneath the memory is partitioned. And the non-uniformness of such an architecture is that this core has a lower latency and higher bandwidth, employing the local let's say connection to the memory, than if it has to go via the interconnect, which enables us to see the machine as a shared memory machine and which takes care of the cache coherency. So that means if this core has to use the interconnect to access memory that's allocated over there, it pays a penalty in terms of higher latency and lower bandwidth. And in particular, if the other cores are also busy, performance can go down. So why are systems built this way? So as I said, all current systems are NUMA systems, and as soon as you look at a two-socket or more socket system, you will find these NUMA properties. The advantage of such a system is that the memory bandwidth scales with the additional sockets. So if you would have just one memory controller for multiple processors, this would always be a bottleneck. It has been a bottleneck in previous systems in the past. And the idea is if that all processors and cores can access local memory, you will get, you will profit from the totally aggregated bandwidth that can become available to the application. And it's also a requirement to build really large systems, so with up to 1028 processors, for example. However, it comes with a higher complexity. So if programmers and users are not aware that the physical memory is partitioned and that there are differences in the memory access performance, the performance of the application that you as a user or programmer care about might not be up to the expectations. So sometimes you can be lucky and just profit from the aggregated memory bandwidth, but sometimes you will suffer from performance penalty because NUMA doesn't play out to your advantage, because the memory accesses are satisfied from remote memory instead of local memory. So the idea of this course is to illustrate this, what it means for a programmer, and what you have to do in terms to come up with an efficient program exploiting NUMA architectures. Before we deal with that, I would like to take a look at the system at least slightly lower level and make sure that you have aware of some tools to understand how the current system or the system that you're using looks like. There are a couple of tools. For example, there comes a program named CPU Info with Intel MPI, or HW-LS, HW-log-LS, sorry, that comes with OpenMPI, for example. But on most current systems, you will also find a tool named NUMA-CTL, which is really simple and my preferred tool to get a high-level overview about the NUMA architecture of the system. So I switch to an example system here. That's a 2-socket Intel Broadwell EP-based system, so pretty up-to-date. And I will execute this command NUMA-CTL-hardware. So NUMA-CTL is telling me I have 2 nodes. So 2 nodes doesn't mean I'm looking at a cluster consisting of 2 nodes, but I'm looking at 2 NUMA nodes. So that means it's a single system, 1 instance of Linux running on it, but we have 2 NUMA nodes, locality domains, because it's a 2-socket system. One node is called 0, the other called is 1, and the tool is telling me the first node has 65-point-something gigabyte of memory, and the other also 65-point-something gigabyte of memory, which is not surprising because the system has in total 128 gigabyte of memory. And it also tells me how the logical processor IDs, as seen by the operating system, are distributed among the 2 NUMA nodes. So we see it's a 12-core processor. The first processor with a core ID 0 to 11 is attached to the first NUMA node, or vice versa. And then the second processor had the core IDs 12 to 23. That's the second processor with a second physical partition of the main memory. And the machine is supporting hyperthreading, so that means these are the other logical threads of the first 12 physical cores of the first socket. And here we have the remaining 12 logical threads. So that also already illustrates a slightly or a tiny problem. So the core IDs are not necessarily consecutive, and this is clearly not a level of abstraction that you as a user or programmer wants to deal with. And I will show that OpenMP can hide these details from you. But so the takeaway message is here we have a 2-socket system with 2 NUMA domains, 65 gigabyte both 65 gigabyte in size. And of course, if you would have a larger system, there's also a distance table. So core node 0 is local to node 0 and remote to node 1 and vice versa. So in a 4-socket or 8-socket system, you could be able to see any further hierarchies if there are any. Okay, so what's the influence of NUMA? So here I'm showing a measurement of the well-known stream benchmark on a admittedly slightly older system. So here we are looking at Intel Westmere processor results with 6 physical cores. So it's again a 2-socket system on CPU 0. On the first socket we have 6 cores, CPU 1 we have 6 cores. And here I'm showing the difference between having the memory all allocated in the 1 NUMA node. So A, B, and C are the arrays being accessed in the stream benchmark. And here they sit all in the memory really close to CPU 1. And that means that threads on CPU, close to CPU 0. And the threads of CPU 1 have to access the memory via the interconnect. In this configuration, we get a memory bandwidth of the 4 different operations of about 18 gigabytes per second. If we distribute the memory, so that means half of the arrays is on the memory close to socket 0, the other half of the arrays is in the memory close to socket 1, and we respect this partitioning of the memory or of the data also in the computation, meaning we distribute the iterations accordingly, so that the threads running here will also will respect the corresponding partition of the vectors. Then we get a much higher memory bandwidth, so like these 40 gigabytes per second in average. And this is what I try to illustrate with aggregated memory bandwidth. So with every NUMA socket, or with a doubling of the sockets in the system, in a NUMA system, in principle you can double the aggregated memory bandwidth if you can only ensure that only that all memory accesses are local. So now the question is, what can we do as a programmer? And with that, before answering that, I would like to illustrate how data is being physically placed on a system by the operating system. So that's a very simple C code. I have a double pointer A, and I'm allocating some data into this pointer A, assuming that n is large, so that I'm allocating at least a few megabytes, maybe even gigabytes of data. And then I'm initializing this data here in an array. So for the dimension of this array A, I'm assigning the value 0 to each individual element. So what happens if I execute this program sequentially? So first, at the point of time at which malloc is called, nothing really happens. So the operating system makes kind of a mental mark or mental note that this application sooner or later might use up to that amount or requested amount of virtual memory. So it will return some virtual address into this pointer A. Only here, later on, when we start, or when the program starts to initialize the data, the operating system has to take action. So with the access to A0, with the assignment of 0, the operating system has to create a mapping of this virtual address A0 to a physical location. The memory is organized in so-called pages by the operating system, so that means it doesn't do that for every individual byte or double in this particular example, but instead in so-called pages, which are an average of size 4 kilobyte. They could be larger if you request that, and some operating system facilities try to come up with more efficient sizes, but by default pages are 4 kilobyte in size. So that means the mapping is created for A0, and then the remaining elements until a size of 4 kilobyte is reached are also mapped to the same memory. And the operating system Linux and all the other current operating systems employ a strategy that's called first touch, because it needs a strategy to decide whether data should be allocated here or there in my illustrative example of a machine. And I'm assuming that the thread performing the allocation and initialization is running here. Then the operating system will try to put the data into this memory here, assuming that there's some data available. If the thread would be running there, data would be allocated over there. And we can exploit this strategy in parallel programming. So what I'm doing here is now I'm parallelizing the initialization. So for so thread 0 is still responsible to initialize A0, but thread 1, assuming I have 2 threads, will be responsible to initialize A at element position n divided by 2. Assuming that A is large enough, that will result in a different page. And if thread 0 is running here and thread 1 is running over there, the data that is initialized by thread 1 will also be allocated and physically placed on the memory that's over there. And that's a strategy that most programs employ in order to exploit NUMA architectures. We have to bind the threads on the machine in a way that we as a programmer think is suitable. And then we have to initialize the data in parallel by the threads in the same way as the data will be processed later on in the code by the threads. So the data access pattern, the parallel data access pattern during initialization and the later on computation should be the best possible match to get the best local distribution on such a NUMA system. So now we have to understand how we can bind the threads, and OpenMP comes up with certain options for that. But before I go into detail, just one remark on the binding strategy. So selecting the right binding strategy depends on several input factors, and you have to understand what your application needs. If it's part of a hybrid application where there's one MPI process per socket, you might not want to distribute the threads over the whole machine, but rather keep them or have them remain on the socket to which the MPI process is bound. However, if you're using 2 sockets or even more on the whole system just with OpenMP, you might want to distribute the threads over the whole machine. The more hardware you use, the more aggregated memory bandwidth might become available to your application. You might profit from combined cache sizes and so on. However, if you put threads closely together, meaning restricting them on the same physical cores, for example, you might see performance improvements in synchronization constructs, because, for example, a lock variable might reside in a shared cache also. So that means there's no optimal binding strategy for all the applications that are out there in the big HPC world. So that means you might want to try with a few of them. And OpenMP comes with a few options to bind threads to the available system. So the facilities that OpenMP offers to perform the thread binding are 2 things, or 2 abstractions. So one is called places, the other is called policies. An OpenMP place is a set of execution engines that can execute OpenMP threads. So that could be a selection of cores or logical cores. And the program or the OpenMP program knows about these places by looking at the so-called place list. That's a list of all places available to the OpenMP program, and it's defined by the OMP_places environment variable. So you can either define them manually. I have an example on that 2 slides later. But in most cases, you can use one of these so-called abstract names, like cores, for example. Here I'm saying I want to have 1 place per core. I will illustrate that on the next slide. Given that we have the place list as an abstraction of the system, we can define a thread affinity policy so that the OpenMP runtime binds the threads to the so-called to the places. Whenever a thread is bound to a place, it can roam freely within that place. So you have the option to decide the granularity of the places. If you want to be a place consisting of multiple cores, the thread can roam across these multiple cores. If you want to pin or bind a thread to an individual core, you have to come up with a corresponding place list. I'll show that in a second. We have 3 strategies in OpenMP to perform the binding. One is called spread, which will evenly spread the OpenMP threads among the places. We have close, which will pack the OpenMP threads closely together, but still on different places. And then we have the master policy, which will collocate all threads into the same or within the same place that the master thread is running on. So what is a place exactly? I have another example architecture here. So the 2 green boxes are meant to represent 2 sockets. The 8 4 boxes are meant to represent 4 cores per socket, meaning 8 cores in total. And then the 4 white bubbles are so-called hyperthreads or logical threads. So it means we would have 4 times hyperthreading per core. If you set the OMP_places environment variable to threads, your OpenMP program would see the machine as 2 sockets times 4 cores times 4 hyperthreads per core places in total. And you can individually bind the threads to every logical or hyperthread in the system. If you would say OMP places equals cores, you would end up with 8 places, 1 place representing every individual hardware core in the system. And if you would set it to sockets, you could direct the threads to one or the other socket because the program would consist of just the 2 places, one per socket. And then in OpenMP, we have either an environment variable or the _procbind clause to exploit the place list, meaning to bind the thread. So I have an example here which will employ nested OpenMP, and I want to illustrate a very typical use case of using the places and policies in OpenMP to control the placement of threads on a system. So here in my example, you see with OMP places, I could individually create the place list out of the logical core IDs, assuming that I want to have full control. For example, in a benchmark situation, that might make sense. But in most cases, people will just say OMP places equals cores, which is also the default on the implementations I'm aware of. And then if I say in a program pragma OMP parallel procbind spread num threads 4, as illustrated here, the first thread without loss of generality running here will create 4 threads, 1, 2, 3, 4, and the spread binding will evenly distribute the threads among the places. Yeah, so it will not be put on P0 to P3, but instead on P0, P2, P4, P6, because we want to make use of the whole machine. The spread policy is different from the other two policies in that it also partitions the place list. So it means here, in the initial sequential part of the program, the thread sees a whole place list. But here, within the parallel region, every individual thread will only see this local partition of the place list. And then if we, for example, call a linear algebra library, which is also parallelized with OpenMP, we could, for example, make use of the procbind close strategy, and again using 4 threads here, so that as illustrated here, for example, this thread will again create 4 threads, and they will be distributed among the 2 places within this place list. And it's guaranteed that thread 0 and thread 1 will run on the same place if 2 threads end up in the same place. So meaning neighbor thread ID will also run as closely together as possible, which is different from several vendor-specific features that are also available in certain implementations. Good, let me illustrate that in terms of performance. So I'm using the Jacobi solver in Open parallelized with OpenMP. It's a very famous OpenMP example code. So it's a parallel region with 2 loops. In the first loop, the current result is stored, and in the second loop we have the compute stencil which reads from the result of the previous iteration and updates then the current result. And then the wraparound we again copy that back. So this is the parallelized with OpenMP. And if I run that on this particular example, I will say OMP underscore places equals core. So I want to have 1 thread per physical core. OMP procbind 1 place per physical core, sorry. OMP procbind equals spread. So I will spread the threads over the machine. And OMP num threads equals 12. So I will use 12 threads on this 24 core machine. I get a performance here of something like 13 gigaflops. So that could be good or bad, and we could go into a performance model here. If we would do that, we don't have time for that, we would see that we are not using the available memory bandwidth. So I have a second code here which doesn't have any difference in the OpenMP Jacobi 1 parallelization of the Jacobi code, but it has a difference in the code which performs the actual initialization of the data. And it's using exactly the techniques that I've illustrated earlier on. So here we have a parallel initialization. Here it is. So I'm saying parallel 4, pragma OMP parallel 4. And what I'm doing here is I'm initializing the actual metrics that I'm working with in the parallel computation later on. And I mean, that's a rather simple code. So here I'm ensuring that I'm using the same data access pattern in the initialization, in the parallel initialization, and in the parallel computation later on. So if I, whoops, if I'm running the same code again with 12 threads instead of 13 gigaflops per second, I'm getting almost 21 gigaflops per second. I could do more tuning and the different number of threads. What I wanted to show here is that parallel initialization is really a key enabler for NUMA performance with OpenMP or any multi-threaded program. So that sounded simple, and of course my examples have been selected in a way that the codes are not too complex. And so do we have everything under control? Where there could be a challenge if you don't know the data distribution or the data access pattern of your code. And there's also a challenge if the data access pattern changes over time. If you don't know the data access pattern, yeah, I have some examples on the next slides or some hints what you could do. If you don't, if you know that the data access pattern changes over time, you could start with a technique that I've just shown, like an a priori or initialist distribution according to the first touch strategy. But at some point, you might want to use explicit migration. So that means after a certain amount of time, or in your simulation, when the data access pattern has changed, you have to rearrange the pages. That's not easily possible. There are some operating system calls, because automatic migration is not really supported in most current operating systems with an HPC configuration. So some recent Linux versions have introduced a feature called auto-NUMA, but on most HPC systems this is disabled because performance is less than optimal or is below that if you have your own control over memory or over NUMA distribution of the data. So if you don't know about the data access pattern in general, let me start with the hint to the move pages, which you can exploit or can employ if the data access pattern changes over time. There's a syscall named move pages, so that's the signature here. You have to specify the process ID, and then you specify an array of pointers addressing the first element of every page, which is about to be moved, and an array of destination nodes. And that means with that you can migrate individual pages from the current NUMA node to the NUMA node specified in the nodes argument. So that's control at a very low level, obviously, but this is probably the only fallback that you can use, or the only technique that you can use if you really want to rearrange the data in the memory. So there's no automatic help with that. If you don't know the data access pattern of your application, or if it really constantly changes over time, still, if you're parallelizing the data access to achieve an initial distribution, might give you better performance. Or you could use a tool like NUMA-CTL, which can do much more than give you information about the hardware architecture, to distribute the pages in a round-robin way. Because of the aggregated memory bandwidth, in most cases it's more profitable, or it's profitable to distribute the pages over all NUMA nodes if you don't know the access pattern, instead of having all the data remain on just one individual NUMA node, because then the memory pass to that single NUMA node easily becomes the bottleneck. So NUMA-CTL-interleave all, and here comes your program, will instruct the Linux operating system to distribute the pages in this round-robin way. NUMA-CTL is worth a look, so it can do many more things. So what it's doing here is it says the memory allocation of the program a.out here is restricted to the NUMA node 0 and 1. So on my example machine, there were only 2 NUMA nodes, but if you're on a larger system, you could restrict it to a subset of the pages, or maybe even only just one NUMA node. And it can also perform the thread binding, so --CPU bind 0 will mean the program is allowed to only run on node 0, meaning NUMA-CTL works on NUMA nodes, meaning all the cores attached to node 0. So with that you can have control where your program and threads run, and from where they can allocate data. So in summary, the strategy is to bind the threads, make sure that they initialize the data that they're going to use later on in the parallel allocation locally. So we have to parallelize the data distribution and then ensure that the threads run bound during the course of the execution of the program. This is supported by OpenMP and works well on most NUMA architectures. And this last few slides showed you some really expert hints on what to do if you have a changing data access pattern or no information about the data access pattern a priori. With that, I'm at the end of this webinar. I hope it was interesting and of help for you. If you want to have support in analyzing the performance of your application, the POP project is there for you. I invite you to take a look at the homepage, but also on the slides you found my personal email address, so if you have questions on OpenMP and NUMA extending the topics of this webinar here, feel free to drop me an email. Thank you very much for your attention.